Alright, so this time we're now going to perform Gaussian elimination with back substitution using matrices. So we have a sample system here, and we're going to perform Gaussian elimination. So first, we write the augmented matrix of the system. So let's say we have A is equal to, so we'll write the coefficients, that's 1, -2, 3, and the constant 9. Then we'll have -1, 3. We don't have a z term here, so I'm going to write 0, then -4. Then here we have 2, -5, 5, and 17. And the goal is to turn this into a row echelon form matrix, which is a matrix that would have 1, then other terms, 0, 1, then other terms, 0, 0, 1, and then other terms. So that we will have like that stepwise manner that we use in equations. So, with that in mind, we would have the following goals. We would need to turn these entries to 0, and also this entry to 0, and we need to turn this entry to 1 and this entry to 1 as well. And again, the reason we're doing that is because we want to follow row echelon form. So therefore, we have now to perform our elementary row operations. So we want this to become 0. So given that this term is 1, how can we combine this term and this term, which is -1, so that this term will become 0? So this is 1 and -1, so that means you can add them so that this will become 0. So that would mean that our first operation would be to achieve row 2, we need to add row 1 and row 2. So therefore, we'll have that. We'll just copy the first row because we are not touching it at this operation. So now let's add row 1 and row 2 to find row 2. So 1 plus -1 is 0. There you go. -2 plus 3 is 1. 3 plus 0 is 3. 9 plus -4 is 5. Then we just copy the third row because we are not touching the third row as well. And there you go. So take note that these two matrices are equivalent because we just perform an elementary row operations and they would mean exactly the same thing, which they are both equivalent to the original system that we are solving. So let's now move that up a little bit. So there. So apart from this becoming 0, we have to turn this to 0 as well. So the question now is, how do we now turn this to 0 given that we can perform with 1 with this entry, or we can perform other operations? One technique is to rely on this one because it would be easier to manipulate 1. So in this case, how would we get 0 rather, for row 3, given a 1 and a 2? So we know that if we would have 2, and to get 0, we can add -2. And to get -2, from 1, we can multiply -2. So following this logic, we can then multiply -2 to this entry, and therefore to the entire row, and add it to this row so that this will become 0 and the rest will follow. So therefore, our row 3 would be obtained by multiplying -2 to row 1, then adding it to row 3. So this is the third elementary row operation mentioned. So since we're touching row 3, I will just copy row 1 and row 2. So now let's have that one. Negative 2 times 1 is negative 2 plus 2, 0. Negative 2 times negative 2 is positive 4 plus negative 5 is negative 1. Negative 2 times 3 is negative 6 plus 5 is negative 1. Negative 2 times 9 is negative 18 plus 17 is negative 1 as well. So this is our new matrix obtained from the previous matrix. And we would continue this series of operations or iterations until we achieve the row echelon form. Now, the next thing that we would like is to turn this to 0, 0. Because this one already is 1, we don't need to turn this one into 1 as well, because this is already our leading one. So what we need is to turn this to 0. So can you see how we can turn this to 0 provided the other entries? Again, our technique is to use the leading one so that it's easier for the computation. As you can see, we can have 1 plus negative 1 and we would have 0. So therefore, I'm going to write it here. Again, for our row 3, we are going to have row 2 plus row 3. Alright. Okay, there. So we'll have 0. First, let's copy first the first two rows. 1, negative 2, 3, 9, 0, 1, 3, and 5. So now, let's add row 2 and row 3. 0 plus 0, that's 0. 1 plus negative 1 is 0. 3 plus negative 1 is 2. 5 plus negative 1 is 4. And there you go. We have already a new matrix. Our next goal is to make this 1 because it has to be a leading one. So we don't have a 1 here in the column, but we can actually divide this by 2 so that this term becomes 1. So that means row 3 can be multiplied by 1/2 because multiplying by 1/2 is the same as dividing by 2. So my new row 3 would be the row 3 multiplied by 1/2. So again, I'm just going to copy the first row and the second row. So now go for the third row. 0 times 1/2 is 0. So I'm going to place that there. 1/2 times 2 is 1. 1/2 times 4 is 2. So there you go. And as you can see, we now have our leading ones. There you go. It now follows our row echelon form. Hence, we now have our matrix in row echelon form, which now we can write this back into a system of linear equations, which we would have x minus 2y plus 3z equals 9, y plus 3z equals 5, and z equals 2. So this now is telling us already that we have a value of z which is 2. So now we can substitute it back here. So we'll have y plus 3 times 2 equals 5. Therefore, we'll have a y value of negative 1. And then going back up here, we'll have x minus 2 times negative 1 plus 3 times 2 equals 9, which we will be provided with x equals 1. So therefore, our solution set is x equals 1, y equals negative 1, and z equals 2. So using matrices, we were able to get the solution for the system. Let us just show the system. There you go. The solution now of this system is actually this one based from the row echelon form of the augmented matrix. And that is how we perform Gaussian elimination with matrices.